So in this video we will examine the electromagnetic wave. As before, we should mention that if you want to understand this video, you should have a look at the previous video, because otherwise you will have difficulties to understand what will come here. Okay. Now let us first put the scenario in place. That is, we choose a infinite conductor, let us say, which have no extension. We put a current on top of this, and this current has an oscillating behavior, sinusoidal variation of the current. This produces a magnetic field around the conductor, which is varying in the same way. You have no electric field because the conductor is neutral. The charges plus minus are equal number, and you have no electric field. So the source of an electromagnetic wave must be just the variation of the magnetic field. Now if you look close to the conductor, you have that the variation of the magnetic field has to be locked in phase with some electric induced field, force more or less. So this is called the near field, with field close to the conductor. When you come a bit further away, you have an induced electric field, which is slightly different. So this is we will examine what happens at a certain distance away, and just look to the induced electric field and how this behaves and how it is created. Okay, to start, we will first have a picture like this to show you, to make you remember the interaction between the downs. So it depends, interaction depends on the angle between the axis of rotation of the two downs. And you have the equation as you see here, cosinus phi, it's psi is interaction which are attracting or repulsing the downs, and you have then sinus psi, which is a transverse force pushing them to the side of each other. So this interaction depends then on the relative position of the rotational axis. Now if we now look to the magnetic field a bit further away from the conductor or from the antenna, then we have a sinusoidal variation of the magnetic field. That is to say, we have a slope of the magnetic field, as you see in this figure here, which are varying. And then what happens is that you have the three downs are moving up or down perpendicular to the conductor, and then you have that interaction between downs will be varying according to the direction of the rotational axis. So let us first, in the first picture here, you see we take the downs which has their rotational axis more or less parallel with the antenna or the conductor, and then you have the magnetic movement of the flux which are varying. And so if you have in this situation, you should have that the downs having a rotational axis in one specific direction will be pushed away, and the downs having the axis in the opposite direction will be attracted. So already from this picture immediately you see that due to the variation of the magnetic field, you will have a separation of the downs depending on the direction of their rotational axis, going to one side and the other. With the distance between them will be the lengths of the wavelengths of the magnetic field. So here you have already a separation between the downs having opposite direction of the rotational axis. Now if you look to this, you will see that since they are separated with one wavelength, half wavelengths between them, you have that in the next step you have that they are pushing on the downs having an axis perpendicular relative to them, that will give them some speed in the direction perpendicular to the conductor. They will go up and down there also, but delayed for relative to the downs having a direction parallel to the conductor. So here you again a separation between downs, and between these two directions of the downs you have then that you push down or up according to that direction, which is a flux of downs perpendicular to the conductor, and that is a magnetic field or magnetic flux, let's say. So now you have that according to the source of the antenna you have the magnetic field which surrounding the conductor, which is varying sinusoidal. This variation of the magnetic field creates a separation of downs having the rotational axis parallel to the conductor, and this separation of the downs in parallel direction of rotational axis will create a flux between them pushing up or down, the downs having the rotational axis perpendicular to the conductor. So this is the reason for the oscillation of the magnetic field or electromagnetic field. You can see in this figure that's what happens here, and you get you can write down this the forces of the electromagnetic field, and you can see that this, if you develop this, you get the equation of Maxwell straight away, and it's absolutely no problem, quite an easy explanation. Then we should say also that the electromagnetic wave must be bigger than the wavelength of electromagnetic field must be bigger than some DAON radius. So let's say something like 10 to minus 17 meter, which is the minimum wavelength of an electromagnetic wave, and there is no limit, upper limit. Now, this is the end of the electromagnetic part of the DAON theory. So let us say that in this thing we should emphasize that the Maxwell equations are not complete. They should be added the induction in a more correct way, and maybe also separate the interaction from the two charges in a way so that you have V over C separated between them. You should not have C square, which induce something that you don't exactly understand what you're doing. If you put V over C separated between two charges, for instance, then things becomes much clearer and you understand what you're doing. So this is some if you write a textbook for school, you should try to follow these lines, I think, to get a much clearer picture of electromagnetic interactions.